Okay, our next topic is going to be a discussion of the CMOS inverter voltage transfer characteristic. We'd like to know kind of where it comes from and what its important features are. And so if you remember, our CMOS inverter circuit was a pair of transistors, one transistor in the pull-down network, which is our NMOS, and one transistor in the pull-up network, which is our PMOS, like so, and their drains are connected together, and their gates are connected together, and this is the input. And instead of calling this like A and Y, we're going to call this V in and V out, because these are going to be voltages, and we're going to be interested in what is a plot of V out versus V in look like. And so I want to just start out by thinking about what would happen if we set V in, let's say, at ground. And let's suppose we had the output held with a voltage source at VDD over 2, which might be 2.5 volts for our case here. So let's say that we have V in at ground and V out held at VDD over 2. Well, what would happen? Well, our NMOS transistor has 0 volts in the gate, 0 volts in the source. It's going to be down as far in weak inversion as we can put it with voltages in between the rails. And so the current through here is going to be like picoamps. So this current might be, let's say, picoamps. Whereas on the PMOS side of things, we've got, let's say, 5 volts on the gate, VDD on the gate, and we've got 0 volts on the gate. I'm sorry, we have VDD on the source, 0 volts in the gate. We've got as much source to gate voltage as we can possibly put on this device. So it's going to be biased up in strong inversion, as far in strong inversion as we can actually put it, with voltages in the power supply range. And so the saturation current that this device would have is going to be maybe on the order of milliamps. Hundreds of microamps, maybe, milliamps. Depends on the size of the device. But for the types of transistors we're measuring in the lab, the NMOS transistor with 5 volts on the gate and 5 volts on the drain would be passing about, 4 or 5 milliamps. The PMOS maybe 2 milliamps or something like that. And if we hold the output at half the power supply, assuming that that's enough to saturate this PMOS transistor up in strong inversion, may not quite be enough to saturate the PMOS transistor, this thing is going to be blasting at saturation current, which is like milliamps of current. This guy, the NMOS transistor, is going to be only pulling at most a few picoamps of current. And so this voltage source that we are holding the output with is going to have to supply, is going to have to eat this milliamps of current in order to maintain the voltage here at 2.5 volts. If we were to then do our standard thing of basically disconnecting the output current voltage source and just letting it find its own level, the question then becomes, where is that current, that excess milliamps of current, where's it going to go? It can't go into the NMOS transistor. Presumably this device is saturated with a saturation current on the order of picoamps. So where is it going to go? Well, the answer, of course, is it's going to go into charging up the parasitic capacitance here at the output node. So that current's going to go into a plus dV out dt. And so then we have to ask ourselves, well, what's going to happen as V out rises? Well, as V out rises, we get more voltage across the NMOS transistor and less voltage across the PMOS transistor. And so that PMOS transistor, if it was starting out in the saturation region, eventually will get into its ohmic region. And what it's going to do is it's going to go deep into the ohmic region with just a tiny, tiny little bit of source to drain voltage across it, just to pass the little tiny amount of picoamps worth of saturation current that the NMOS transistor wants. And so this voltage here, V out, is going to be really, really close to VDD, maybe only a few, 100 microvolts below VDD or something like that. And so that's how, with the voltage on the input at ground, the output is going to be up near VDD. If we were to imagine the opposite situation, where we have the input, let's say, connected up to VDD now, and let's put our voltage source back here, maintaining V out at VDD over 2. Well, now we have the opposite sort of situation, where we have the maximum VGS on the NMOS transistor, and so the saturation current will be like milliamps. And we have basically no source to gate voltage on the PMOS transistor, and so we're going to have, again, maybe a few picoamps of saturation current there. And so now this voltage source is going to have to be supplying the milliamps of current required by the NMOS transistor. And if we were to, again, let go, disconnect that voltage source, where's that excess milliamps of current going to come from? Well, it's going to come from, again, our parasitic output capacitance. And we're going to be discharging, so we're going to have a minus dV out dt. And this voltage is going to start to drop. That's going to put more voltage across the PMOS transistor, but it's going to be driven further into saturation. And driving it further into saturation just doesn't do very much to the current. We may get a little bit of increase due to the early effect or something like that, but it's not going to represent orders of magnitude that we need to make up the difference between picoamps and milliamps. And so having less voltage across the NMOS transistor, however, will drive it closer to the ohmic region, so it'll move down its saturation characteristic for a while, and then eventually it'll turn that knee when it hits VDS sat, and the current will start to decrease rather precipitously. And eventually, again, we're going to wind up with just enough drain to source voltage across the NMOS transistor so that we can pass whatever amount of saturation current the PMOS transistor is passing. So again, it may only be like 100 microvolts or 10 microvolts or something like that across this transistor. We're going to be very near ground. And so that's how, with a high voltage on the gate, we wind up near ground. And so that's kind of 2 points on the characteristic, but what we would like to do is to construct, what the whole curve looks like. And so to do that, what we're going to do, I'm going to sketch the voltage transfer curve maybe over here somewhere. Okay, so this is V out versus V in. Let's say this is VDD, and this is VDD. And we've got kind of this box here, and then we've got the identity line. This is V out equals V in. And so we've got 2 points on this curve. We got this point, and we got this point. And we're going to use 2 other plots here to help us out. One is going to be a plot of, I'm not sure if I have enough space to do this. I'll give it a shot. I'm going to call this I versus V in. So this is the current. Let's call this IP. Actually, let's use colors. Let's try using some colors here. So you get I, N, and I sub P. And this is going to be, say, I sat N and I sat P. And then we're going to have another plot here. Which is going to be V out on the horizontal scale. And we call this IN and IP. Okay, so these are going to be our gate characteristics, right? So this is a plot of saturation currents as a function of gate voltage for the NMOS and the PMOS transistor. And here we're going to have drain characteristics. So V out is the drain voltage, common drain voltage of the two transistors. And so we looked at these characteristics in Lab 5. And so on a linear scale, the saturation current for the NMOS transistor is going to start out down at 0. And then at VTN, or VT0N, it's going to start to increase and open up like a parabola that goes up. Something like that. And then maybe this is VDD here. We'll put VDD here. And for the PMOS transistor, up near VDD, that's when it's in weak inversion, the current's basically 0 down until we get to about a threshold voltage below VDD, like 4.3 or something like that, and then it's going to open up parabolically this way, something like that. Maybe it's not going to get quite up as high as the NMOS characteristic does. And what we're going to do is we're going to consider different input voltages. And we're going to look at the drain characteristics that correspond to these saturation currents and get different points here on this curve, because where those drain currents actually cross is going to be where KCL finds a way to satisfy itself in this circuit. Okay, because these two currents have to be equal to each other. IN has to equal IP in the steady state. And the place where those drain characteristics will cross is the place where KCL is going to be satisfied. Okay? So let's imagine that we're somewhere down here with VG. Okay? So here we have a saturation current in the PMOS transistor of about here. Okay, so we'll transfer that over here. And we have a saturation current in the NMOS transistor, which is way down here. Okay? So the PMOS transistor is going to be having a characteristic that looks maybe something like and so there's a parabola that opens down, something like that, and then it hits the saturation part of its characteristic, and it's going to be looking something like that. So at 0 VDS, it's going to go down to 0, but as it gets down toward ground, it's going to be saturated. The NMOS transistor's drain characteristic is going to be pretty much indistinguishable from 0 on this scale. And so the place where they're going to cross is pretty much what we said, up here at near VDD. And so the output voltage is going to be up here. Actually, that was something like over here somewhere, right? So the input voltage was maybe like that, and so again, the voltage is going to be up near VDD. Well, nothing really interesting is going to happen until we get past the threshold voltage, and maybe, let's say we're operating here, where we're just starting to get above threshold with the NMOS transistor or something like that. Well, we're on a different set of drain characteristics. Now we have a different set of gate voltages. Here the PMOS saturation current is like down here, so that's here, and the NMOS saturation current is here, which is like maybe here somewhere. And our PMOS drain characteristic is going to look something like this. It's going to saturate at a slightly lower voltage, while the NMOS transistor is going to be coming up and maybe look something like that. Well, the place where they're going to cross is right here. So now we've moved down away from VDD a little bit, and we're maybe out to here on the gate. So that's going to be maybe something like that. So we're coming down off of VDD, but it took us a while to get there. So now if we move over a little bit further, let's say to this point where these two curves actually cross, well, at that point, both of these drain characteristics are going to have the same sort of saturation current value. And if one pops up a little bit and the other one pops down a little bit, the place where they cross is going to switch from near VDD to near ground very, very rapidly. So this is about, say, right here. Our saturation current level maybe looks like that. And our NMOS saturation current level is about the same, only its characteristic is going to look more like this. And so, who knows precisely where they cross? We could denote that by just having kind of a vertical line here. And then if we move over a little bit further on the gate voltage, say up to here, maybe a little bit to the left here, where we're still above threshold with the PMOS, but not by very much. Well, we're down here. Something like that for the drain characteristic of the PMOS. And now we're up here for the NMOS. And so the NMOS is maybe doing something like this. Saturating at about that level here. This is the ohmic region down here. Well, the place where they're going to cross is down here near ground now. And so what we're going to do is get kind of into a regime where maybe we're right here on the gate voltage. It's going to cross right here. And then once we get above the threshold voltage on the gate for the PMOS transistor, and the PMOS is in weak inversion, well, now the blue curve is on the x-axis, or on the x-axis the blue curve is down here. And see, up at this level, we're talking about the NMOS curve being up here somewhere. And so they're going to be crossing practically down at ground. So that might be up here. And so we're going to get a characteristic that looks something like this. And we saw this in the simulation tutorial that I posted last Tuesday in advance of lab. And so we have this these shallow regions where up here the NMOS transistor is in weak inversion and the PMOS transistor is in weak inversion down here. And then we've got this area where they're both kind of in strong inversion, and this steep part of the curve is where both of the transistors are in strong inversion and in saturation. And I've drawn this very, very steep here because our drain characteristics were very flat by hypothesis. That's kind of our zeroth order assumption. Now, if they had more of an early effect, so that there was more of a slope in the saturation region, that would make this curve less steep here in the transition region. And so I want to talk about some interesting features of this voltage transfer characteristic that that we can see. And maybe the best thing to do would be to move this over a little bit here. So let me quickly kind of sketch this over here. So this is V out, V in, VDD, VDD. Here's our box. Here's the identity line, V out equals V in, and then our VTC, which is maybe like doesn't have a backwards bending characteristic. Let's just say it goes something like that. The place where this VTC crosses the identity line has a special name. It's labeled VM. And VM is called the transition threshold. It's basically the point at which the output is equal to the input voltage. So this might be VDD over 2, it might not be VDD over 2. It depends on the relative sort of strengths of these two transistors. If the NMOS transistor is a little bit stronger than the PMOS transistor, then it's going to be skewed to the left. If the PMOS transistor is a little bit stronger than the NMOS transistor, it's going to be skewed a little bit more toward the right. And so the transition threshold would be a little bit lower or a little bit higher. So that's one key point on the curve. The slope of the tangent line to this characteristic is always negative, right? So it's always sloped down. And there will be a place, so here the slope is almost 0, and here the slope is almost 0, very small. Here the slope is actually quite steep. There will be a place in between where the slope of the tangent line is -1. And there will be another point down here where the slope of the tangent line is -1. And those are special points. So those points where that slope of the tangent line is -1. So this one is called VIL, and this one is called VIO. VH, and then this point here is called VOH and VOL. And basically, this range of input voltages is considered a 0, and this range of input voltages is considered a 1. So logic low, logic high. So anything in this range is considered a reasonable logic low. Anything in this range is considered a reasonable logic 1. And so the question is why? Why is that a reasonable thing to do? You know, why is it the place where the slope of the tangent line here is -1? Well, there's actually quite a good reason for that. Suppose you've got some logic signal and it's got some noise on it, and I put it through a gate with a voltage transfer characteristic like this. Well, if I'm in this range or I'm in this range, any hash on my input signal will not be amplified, it will be attenuated, because the slope of the tangent line of this characteristic is the gain of the circuit as an amplifier. Right, so this is V in, this is V out. If I wiggle around down here by some amount, that gets mapped by this curve into wiggling around the output by a smaller amount. Same is true over here. If I wiggle around by over some range here, that gets compressed into wiggling around in a smaller range on the output. So in this region that I've labeled 0 and 1, basically the inverter attenuates those variations in the signal. So it basically attenuates what would be considered noise in the signal. Whereas here in the middle, this is steep, and so if I wiggle around in here somehow, my output's going to bang around by quite a lot. Okay, so these ranges of input voltages that we consider valid logic low and valid logic high, if we operate in those ranges, we're going to have nice quiet outputs, and the gate will basically squash that noise for subsequent stages. The other interesting thing you'll notice is that the range of valid input levels gets mapped, let's say 0, gets mapped into a much smaller range of output voltages. So a wide range of input zeros get mapped onto a much narrower range of output voltages that would be considered a 1. And this is the output range that's considered a 0. And so same is true over here. This much wider range of input voltages gets mapped into a much narrower range of output voltages that's close to 0. So if I put in sort of an input signal that's not quite near the rails, by the time it goes through one of these stages, it's going to be much nearer to the rails. And if I put it through a second stage, it's going to be practically at the rail. And so that property of this inverter voltage transfer characteristic is called level restoration. So we have two key properties. One is noise immunity, or noise suppression. And level restoration. So this comes from the fact that the VT dV out dV in is less than -1. Let's say the magnitude of dV out dV in is less than 1 for valid logic levels. And in this case, we have basically the output near to opposite rail than the input. So if we pass a logic signal that's kind of not quite at the rails, maybe even in the middle of the rails, through several stages of inversion, we'll get the logic level restored to a nice strong 0, a nice strong 1. Okay, so those are key characteristics of the CMOS inverter. In fact, if we were able to somehow build a circuit that had a VTC that maybe looked more like, say, something like this, where maybe it had some funky curve that looks something like that, where we had a transition threshold here, Vm and Vm, and we had a shallow slope here in the middle and steep slopes here on the edges. We would have just the opposite sort of properties. And it turns out that if we had a logic gate that looked something like this, we couldn't actually build reliable digital systems with it, because it would have exactly the opposite properties as the normal inverter characteristics. So we would get noise enhancement, so any little variation in the voltage levels here in the range that correspond to 0 and 1 would be amplified at the output, so it would enhance the noise. And any, if we put an input signal that's in somewhere in the middle of the rails, actually the output will get closer to Vm, and so we're actually going to be moving the logic levels toward Vm instead of toward the rails. And so this is a recipe for disaster. So we actually could not make reliable digital systems with many, many stages of logic with this type of voltage transfer curve. So the shape of this curve, and the fact that this has a steep part in the middle and shallow parts on the end, is actually quite vital for building reliable digital systems. So I think that's going to be it for this particular segment.